Welcome back to the Decentralized Application Development Crashcasts. I'm Sheila, and I'm here with Victor. Before we dive in, we'd love to hear from you. If you're enjoying our podcast, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you.
That's right, Sheila. Your feedback means the world to us. Now let's get into today's topic. We're continuing our journey through Chapter 3 on distributed hash tables, or DHTs. We've already covered the Chord and Kademlia algorithms, and today we're exploring other DHT algorithms.
Exactly, Victor. But before we jump in, I've got a quiz question for our listeners. Here it goes. Which DHT algorithm uses a d-dimensional coordinate space for routing and is known for its ability to support range queries? Think about it, and we'll reveal the answer at the end of the episode.
Ooh, that's a great question, Sheila. It touches on some unique aspects of DHT algorithms that we haven't discussed yet. I'm excited to see if our listeners can figure it out. For now, let's start by quickly recapping what a DHT is for those who might be joining us for the first time.
Good idea. A distributed hash table is like a giant decentralized address book. It's a system that allows us to store and retrieve information across a network of computers without any single computer being in charge. We've talked about Chord and Kademlia, which are two ways to organize this address book. What other methods should developers be aware of, Victor?
Great question. Let's start with an algorithm called CAN, which stands for Content Addressable Network. CAN takes a unique approach by using a virtual multidimensional space to organize nodes and data.
That sounds interesting. Can you explain how this multidimensional space works? It seems quite different from the ring structure we saw in Chord.
Absolutely. Imagine a big cube divided into smaller zones, like a 3D grid. Each computer in the network is responsible for a specific zone in this space. When you want to store or retrieve data, you use a special formula to turn your data into coordinates in this space, and then find the computer responsible for that area.
I see. So it's like each piece of data has an address in this virtual space. How does this compare to Chord or Kademlia in terms of efficiency?
Good question. CAN's method of finding data can be more efficient in some cases, especially as we add more dimensions to our virtual space. However, it comes with its own challenges, like keeping the zone structure organized as computers join and leave the network.
That makes sense. Are there any real-world uses of CAN that developers should know about?
While CAN itself isn't as widely used as some other DHTs, its ideas have influenced other systems. For example, some peer-to-peer networks for sharing files have used similar multidimensional concepts for efficient data distribution.
Interesting. What about other algorithms? I've heard of something called Pastry. How does that work?
Pastry is another fascinating DHT algorithm. It combines ideas from both Chord and Kademlia. In Pastry, each node has a unique identifier, and routing is based on matching parts of these IDs.
Matching parts? Can you give an example to help our listeners understand?
Sure. Imagine node IDs are like phone numbers. If you're trying to reach 555-1234, Pastry would first try to find a node that matches the most digits, like 555-1230. If that's not available, it might go to 555-1200 and so on. This approach allows for very efficient routing, typically finding data in just a few steps.
That's a great analogy, Victor. It sounds like Pastry might be easier for developers to understand compared to some other DHTs. Are there any notable uses of Pastry?
Indeed, Pastry has been used in various academic and research projects. One notable implementation is FreePastry, an open-source version in Java that's been used for building peer-to-peer applications and studying DHT behavior.
Fascinating. Now, I've also heard of something called Tapestry. How does that fit into the picture?
Tapestry is quite similar to Pastry in many ways. It also uses prefix matching for routing, but with some differences in how it handles network locality and fault tolerance. One interesting feature of Tapestry is its focus on minimizing delays by considering the physical network layout when routing messages.
That sounds really useful for real-world applications. Speaking of which, Are there any common misunderstandings or pitfalls developers should be aware of when working with these different DHT algorithms?
Absolutely, Sheila. One common misunderstanding is that all DHTs are equally suited for all tasks. In reality, the choice of DHT can significantly impact your application's performance and scalability. For example, Can might be great for applications that need to search for data within a range, while Pastry or Tapestry might be better for applications that need quick lookups.
That's a great point, Victor. It reminds me of the old saying, choose the right tool for the job. Do you have any tips for developers on how to choose the right DHT algorithm for their specific needs?
Certainly. I'd recommend considering factors like how big your network might get, what types of searches your application will do most often, and how much delay you can tolerate. Also, look at how well-developed and supported each algorithm is. Sometimes, a well-supported version of a slightly less optimal algorithm can be a better choice than a theoretically better but less tested option.
That's excellent advice, Victor. Now, before we wrap up, I think it's time to reveal the answer to our quiz question. The algorithm that uses a multi-dimensional coordinate space for routing and supports range queries is CAN, or Content Addressable Networked. Addressable.
Great question and explanation, Sheila. I hope our listeners found that interesting. To summarize today's episode, we've explored several DHT algorithms beyond Chord and Kademlia, including Can, Pastry, and Tapestry. Each of these algorithms offers unique approaches to organizing and finding data in distributed systems, with their own strengths and trade-offs.
Absolutely, Victor. We've seen how Can uses a multi-dimensional space, while Pastry and Tapestry use clever ways of matching IDs for efficient routing. Remember, the key takeaway is that choosing the right DHT algorithm depends on your specific application needs and priorities.
Well said, Sheila. And to our listeners, we hope you've enjoyed this deep dive into DHT algorithms. If you found this helpful, please visit crashcasts.com and consider joining our Discord community. Your support on Patreon helps us keep producing high-quality content, and don't forget to subscribe and rate our podcast.
Thanks, Victor, and thank you all for listening. Until next time, happy coding.